This is William Dillon, Associate Professor of Electrical Engineering at UTA, and we're going to talk about sinusoids as used in electric circuits. One of the frequent activities that we must do with sinusoids is adding two sinusoids. This is a little cumbersome when they are functions of time, and so we're going to show you how to do this by using phasors. In the problem in front of us, we have two sinusoids. V1 is the red trace that you see, and it's a sinusoid expressed by 100 sine of omega t, where you see omega is the radian frequency, and there's no phase shift on V1, so it starts at 0, and its peak value is 100, and it shows one full cycle of this. The other sinusoid that we're going to add is the blue trace. We're calling that V2, and it's got a magnitude of 80, but it also has a phase shift. It's lagging behind by 60 degrees. Now I'm putting this in degrees, even though when evaluated this would all be in radians, but we can understand degrees better. When these two functions are added, the red wave and the blue wave, if you added them point by point, which would be awfully tedious, you would get V3, which is the magenta colored sign, and that shows up at a peak of around 152. And of course the phase shift is a little off too. It's not at 0 and it's not at minus 60. It's kind of somewhere in between, as you can see, and we'll find that value pretty soon. Since we're going to be converting these to phasors, we're going to have to see how to change a time-varying sinusoid into a phasor. If we do that, and I'll show you how in a minute, the sinusoids would be represented like you see in this little diagram. Notice V1 is pointed straight down because that was a sine with no phase shift at all. And so if you rotate it counterclockwise around the complex plane, its projection on the real axis would be a sine, just a plain sine starting at 0, okay? V2 would be the phasor representing the second wave, 80 at where it's at minus 60 degrees, but that shows up over here in the third quadrant, because if you took that sine wave, then it would start out negative projection on the real axis and finally hit its get to 0 and then start going positive again. Okay, if you add the red phasor and the blue phasor, we can show that sort of by imagining sliding the blue phasor V2 all the way down and tacking it on to the end of V1. The resultant is V3, and that's what we're going to do numerically. All right, so V1 plus V2 shows up as V3, and it's also down in the third quadrant, and we'll have to convert that back to a sinusoid pretty soon. Okay, so this is what you would see on the complex plane, but we want numbers, so let's see how that is done. Okay, here's what we do to convert sinusoids into phasors. If we start out with a sine function, f of t has got some peak value times the sine of omega t plus theta. Let theta be the arbitrary phase angle. It could be positive or negative. To go into phasor mode, we would do this. The real part would be the peak value, f max, times the sine of theta. Notice we got rid of omega t when we go to phasors, but we'll put it back in when we need to. Also, the imaginary part would be minus the peak value times the cosine of theta. So that's a minus j, peak value times the cosine of theta. And of course, as a phasor, that would be peak value at an angle of theta minus 90 degrees. As you know, mostly phasors are based on the cosine. Now, if we actually have a cosine function, f of t is some peak value f max times the cosine of omega t plus theta. Well, then our phasor would be the peak value times the cosine of theta for the real part, and peak value times the sine of theta for the imaginary part. Or that would simply be, in polar form, a peak value f max at an angle of theta. So that's the operation that we do so that we can combine them as phasors, and then we can go back to the time domain when we need to. So here's where we'll add them, and we're going to continue with this numerical example. First of all, V1, that was the red curve. It showed up as 100 sine omega t, no phase shift, so the phase shift is 0. Using our little formula that we talked about just a few minutes ago, that would be the peak value of 100 times the sine of 0 degrees, which is 0, so there is no real part here. And then minus j100 cosine of 0 degrees, and of course the cosine of 0 is 1, so you get a full minus j100. That's why the red phasor pointed straight down on the complex plane. Our second value, V2, was a peak of 80 and the sine of omega t minus 60 degrees. So our theta here is minus 60. So here's the real part is 80 times the sine of minus 60 degrees. That's going to be the real part, which will be negative, because the sine of 60 degrees, the minus 60 degrees, is going to be minus the square root of 3 over 2, and you'll get this 69.28 for its real part. And then the second part, the imaginary part of V2, would be minus j80 times the cosine of minus 60 degrees, and the cosine of minus 60 degrees is 1/2, a positive 1/2, and so we already have a minus j, so half of 80 would be 40, and add this to the minus j100, and the combined parts are a real part of minus 69.28, or call it 69 minus 69.3. The imaginary part totals up as minus j100. Now, that's a complex number in rectangular form. If we put it in polar form, we would get 156.2 at an angle of minus 116.3 degrees. And of course, we know how to do that conversion. It's just a right triangle, and 156.2 is the square root of the sum of the squares of the real and imaginary parts. The angle we get by taking the arctangent of 140 over 69.2, remembering that that's in the third quadrant, so it's minus 116.3. Now, our object was to get this back into the time domain, so we could literally do this. V3, the combination of those, the addition of those two phasors, V1 and V2, has a peak or a maximum value of 156.2, and we can simply slap on cosine and then put back the radian frequency of omega t with the phase shift of minus 116.3 degrees, and that is a sinusoid. Now, if you want it to look like a sine, we can do that too. All we have to do to change this cosine to a sine is to add 90 degrees to the angle here, and then it comes out 156.2 times the sine of omega t minus 26.3 degrees. And that way we can have our choice. It can be a cosine or a sine wave. Usually we're going to want the cosine. And that's how we can add sinusoids in the time domain, by switching over to phasors, doing the math where it's easy, and then back to the time domain.